We understand what we can do if we know the value of the equilibrium constant, how we can solve for how much a reaction will proceed until it reaches equilibrium. But that still leaves the question of how we figure out what the equilibrium constant is. In the example we've worked so far, I've given you the value of the equilibrium constant, and that's often something you could look up, but it's also something you can determine for yourself if you need to. So we know so far that the equilibrium constant can be calculated as this product of partition functions raised to their stoichiometric coefficients. For example, for our favorite reaction so far, H2 and Br2 making HBr, the equilibrium constant is partition functions of HBr squared divided by partition functions of H2 and Br2. Those have to equal K. So the value of K, if we want to know what the value of K is, we can find it in several different ways. You could determine it experimentally. In fact, that's often what's done. For example, one of the examples we've worked before, if we do that in reverse, let's say we don't solve for how much the H2Br2 reaction will proceed in order to reach equilibrium. Let's say we just throw 1.5 moles each of H2 and Br2 and HBr into a container, let them react how they want, and then measure when we're done that there's only 0.1 moles left of H2 and Br2, and they've converted into a total of 4.3 moles of HBr. We can throw those numbers into the reaction quotient, and 4.3 moles squared over 0.1 moles and 0.1 moles, calculate what that equals, and we've obtained experimentally the fact that the equilibrium constant is equal to 1800. So that's what we would do if we want to use experiment to determine the value of an equilibrium constant. And like I said, that's fairly commonly done. But the equation that gives K in terms of partition functions tells us that we can also use the partition functions themselves to determine the equilibrium constant, to predict it without doing an experiment. There's a third method, which I won't spend much time on right now. We'll talk about that in the future, but you can also use the Gibbs free energy of a reaction to predict the equilibrium constant. So I'll mention that now, there, just so that we have all three methods listed. But let's focus a little more on how we would use partition functions in order to calculate a partition function. So for the H2 and Br2 reaction, all of these are diatomic molecules. We know from quantum mechanics and statistical mechanics a fair amount about diatomic molecules. We know, or we've certainly approximated, that the partition function for any diatomic molecule consists of one piece due to translational energy, one piece due to rotational energy, another piece due to vibrational energy, and if we're considering electronic excitations, a piece due to those electronic excitations. Each of those we've studied in some detail. The translational energy contribution to the partition function that we got by thinking about the particle in a box, that worked out to be this de Broglie wavelength to the -3 times the volumes. This collection of constants for the molecule, also involving the temperature, raised to the 3/2 power times the volume. That's the translational partition function that we've seen. The rotational partition function, and if we're in the classical limit, then that worked out to be just T divided by the rotational temperature, where we also include this symmetry number to distinguish between symmetric molecules that have sigma equals 2, like H2 and Br2, and asymmetric molecules like HBr that just have a sigma value of 1. That we got from doing the rigid rotor approximation. The vibrational partition function, when we studied the harmonic oscillator, we found that the vibrational function was this collection of e to the minus vibrational temperatures divided by T in this particular combination. And then lastly, the electronic partition function. Since electronic excitations, electronic energy levels are so much higher than the ground state, usually those don't contribute very much. The excited electronic states are not accessible at KT for reasonable temperatures. So the only thing we have to consider is the degeneracy G of the ground state. If the ground state is singly degenerate, then G is equal to 1, and we can effectively ignore the electronic partition function. If the ground state is doubly degenerate or triply degenerate, then we would include a 2 or a 3 to account for that degeneracy. So this equation that I've written down, the translational, rotational, vibrational, and electronic partition functions, has made a number of assumptions. We've assumed that the translational and the rotational partition functions are behaving classically, We've also assumed that the harmonic oscillator and the rigid rotor model are applicable here. We could write down more accurate versions of this equation that are even more complicated if we were considering anharmonicity or centrifugal distortion or other effects. There's one additional caveat we have to think of with this partition function, which is that this equation works fine if we're talking about the partition function of any individual molecule, but we have chosen a particular zero of energy when we write that equation down. The vibrational partition function in particular, every time we write down theta vibrational is related to the vibrational frequency of this harmonic oscillator. So the ground state energy, the 0 point energy, is 1/2 h nu, written in terms of a frequency, or 1/2 times k times theta vibrational, written in terms of the vibrational temperature. That energy is calculated relative to the zero of energy taken to be the bottom of the well for this vibrating diatomic molecule. So it's 1/2 h nu above the bottom of the well. For Br2, the bottom of the well may be here. For H2, the bottom of the well may be somewhere different. And each of these molecules we've thought of as having an excitation of energy of 1/2 h nu above the bottom of the well. But those bottoms of the wells are in different places. Effectively, we've defined two different zeros of energy that are inconsistent with one another. So when we're treating more than one molecule at the same time, H2 and Br2 and HBr all in the same system, then we have to define a zero of energy that is the same for each of the species in the system. So if we take the zero of energy to be when the molecules are fully dissociated, when the H2 molecule dissociates and the H atoms are far away from each other, the Br2 molecules are dissociated, so the Br atoms are far away from each other. When nothing is interacting with anything else, we call that the energy of zero for the system. Then what that means is the ground vibrational energy of the Br2 molecule is actually lower than zero by a bond energy of a Br2 plus an additional 1/2 h nu for the 0 point energy of that molecule. Likewise, for H2, the energy of the ground state H2 molecule is negative the bond energy for H2 plus 1/2 h nu for the H2 molecule. So to keep the zero of energy consistent, we have to add these dissociation energies, these bond energies, into our expression for the partition function, where before we just had 1/2 h nu or 1/2 k theta that showed up in the partition functions. Now we need to include 1/2 h nu or 1/2 k theta and also a e to the minus negative of the negative of d sub e over kt. So that turns into e to the positive dissociation energy over kt. So effectively all that's happened is this expression for the partition function for the harmonic oscillator has been modified by throwing in one additional term which corrects the zero of energy that we were using to the zero of energy that we're now using to keep it consistent for every molecule. So this second expression, I'll go ahead and put a box around that one, is the one that we should use to calculate individual partition functions for molecules, diatomic molecules, if we want to use them to calculate the partition the equilibrium constant. So the goal will be, and we'll do it in the next lecture, calculate individual partition functions using this expression for each of the molecules in our reaction, H2 and Br2 and HBr, throw them into this expression for the equilibrium constant, and we can predict the value of the equilibrium constant using these statistical mechanical expressions.